now I should go over the preparation for the final exam.
Yeah.
Okay, I think that essentially the final exam will be like a combination of all three exams, right? In one, it will not be 3 times longer. We will have 2 hours, okay? But you should have some kind of vision on all the material, okay? So you should be able to connect between those topics, which I was always trying to do in my presentation, so that you see everything from above, how the things are connected one to another, so that you don't see them isolated. Okay? So then try to kind of see it from above, and I will ask you some questions. I will still be asking questions in individual topics, but it's more like connecting the things together. Okay?
Do I have a date for something like that?
I don't know. I assume that it should be on the 9th, but I don't know.
It's like Wednesday or 10:30.
Yeah, I think that's on the 9th.
It's online.
It is all of the people who have the classes now, this time, have them on the 9th, I believe. There is some rule how to calculate it actually, which day it is. Okay, so that's pretty much this. So, and then in terms of the style, again, you will be asked similar questions like I was asking you, okay? So don't expect something completely different. It will be similar. Again, maybe I can ask you some problem here and there. I will probably ask you some problem from quantum mechanics, some quantum well, or so. Ask you to explain something in the atom, just very simple. Tell me something about molecule, what are molecular orbitals, how the Slater determinants look like. I will not tell you, show me Slater determinants. I will tell you, show me a wave function for a molecule, okay? And you have to tell me that it's a Slater determinant, okay? Something like this, okay? And so, of this kind. And then the StatMech we just did last time, so you still have it in your fresh mind. And maybe I will add a problem or so, maybe one problem or two in the last part, which we didn't do, this kinetics, okay? Very simple again, something very, very basic, okay? I don't know, I might post. By the way, how is it with the homeworks? Did you give me all of them already, or do you still have some? Can you, okay, later you can collect. Okay, so that's the kind of style. So now I will try, because we have 2 hours, I will maybe go faster. I don't know if I will manage everything. I might skip over the last part because it is not so essential now. Yeah. But the style is the same, okay? So you will see. So I mean, there is nothing to say here. If you have any questions, ask me anytime, okay? Okay, it's again, it's just kind of empty for us. I just want to go over it. Okay, again, I will not be asking you about this. But there is this connection, right, between classical and quantum. We start from classical Hamiltonian, which is in fact the kinetic energy plus the potential energy, okay? In the last exam, I'm just sitting with the TA to correct the last exam. You have the energy of the microstate classical is the Hamiltonian, because the Hamiltonian, classical Hamiltonian is the energy, right? In the quantum case, it's an operator. It's the energy, it's the total energy of a group of n particles, okay? So it basically, if you know the distribution of classical particles, what are the x, p, you know the total energy, you know the microstate of these particles, right? And then it goes in this exponent and it gives you the probability of that microstate, right? It's very simple. Maybe I'm checking that I can. Okay, so then that's all. So this is the connection between this classical Hamiltonian and the quantum. We have operator here, and again we have the probability that a microstate of some quantum kind with some kind of average momentum or so, average coordinate would be populated. Okay, so that would be the same, except that in the quantum it has more like operator form. The distribution has an operator form, and it's a sum over different quantum states with different probabilities. And again, the energy of the microstate is giving us the probability of those microstates. So I connect you already to the statistical mechanics you see here, starting from this classical slide. Yeah, this you can skip over. Yeah, I don't care about this. I don't think that we need this. Yeah. Okay, I will just skip over this. You see, this is the Bose-Einstein distribution. In fact, we got it's like this. We have three distribution. One is the Maxwell-Boltzmann, and the Maxwell-Boltzmann doesn't have this one. Okay, if I don't have the one here, then it's the Maxwell-Boltzmann distribution. It's the Boltzmann distribution, in fact, over the energy for classical particles. Okay, and if I have -1, it is true for bosons. It's the Bose-Einstein distribution. If I have +1, it's the Fermi-Dirac. It's for the fermions. So this one that tells you if it's for fermion, bosons, or classical particles which are distinguishable. Okay, that's all. And so then you have all distribution in one. And in fact, is the blackbody radiation, which you probably thermal radiation. If you multiply it by this constant, it's not constant, it's another function, but it is basically the heat or the flow of particles with different wavelengths in the blackbody radiation. I just wanted to connect it again, so that you have the statistical mechanics just in this right away, and those are the distribution over these energies, or I cannot say velocities because photons have all the same velocities of light. This is constant, but energies of photons, right? And then you have it all connected to the previous stuff that we did. Yeah, this is perfect. I will skip over. Yeah, I mean the Bohr atom is also useful because the Bohr atom essentially has these discrete states, right? Discrete levels, and they are kind of introduced intuitively by some constant like this, but in fact it is related to the discreteness of the number of de Broglie wavelengths on the orbit. So this is basically telling you that that number of de Broglie wavelength must be discrete. That's all. Okay. And then once you use these rules, right, where we have to prohibit the radiation, then we get pretty much the orbit radii from the fact that the radial force must be 0 on the orbit, right? For the stability, it's like a satellite. To make it stable, the radial force must be 0, and from this, this is the attractive force. In this case, it's Coulombic, plus the repulsive, which is centrifugal, right? This is the centrifugal force. I think it comes from the previous lecture, from the solution, and this is the angular momentum squared. Then if these two forces cancel, then we get the radius of the orbit from this. Okay, and then we can get the energies after we put it in the kinetic energy and the potential energy. We get the angular momentum, right? We have angular momentum, and from the angular momentum we can calculate the kinetic energy, and from the radius of the orbit we can calculate the potential energy. If you sum it, you get the quantization of hydrogen. Well, it's not hydrogen, but the Bohr atom. Okay, kind of simple understanding, and it's all connected, right? You see, you don't have to, nobody is sleeping here in this one? I know, I'm just asking. Okay, if you have any questions, just ask me. Okay. Yeah, I mean, this is extremely important, right? Because the Broly wavelength kind of idea connected the wave and corpuscular nature of matter, right? Because whenever, I mean, momentum is a feature which is associated with some corpuscular kind of character of matter, that some localized piece of mass has some momentum, but wavelength is a wave nature of matter. So here it connects the two characteristics into one. That's what is beautiful on this equation, which is so simple. So then from this formula, which is true for any particle irrespective of the nature of the particle, as long as we know the momentum of the particle, we immediately know the wavelength, and we can then tell how it will behave, because the wavelength already tells us how it will interfere with itself, right? If there is some kind of constriction, how it will interfere, if it does or not, and potentially the stability in the Bohr atom, the wavelength also tells us which orbits are stable, as we just said, right? So you have discrete number of wavelengths on the orbit. Okay? It's all clear, right? I don't have to explain. Yeah, and then we try to do the analogy to classical mechanics to introduce it. I don't have time for this again, but it's simple. We just use the classical wave equation. We use the separation of the variables, which is possible when the terms are constant, this prefactor, and when there is no term which is mixing, kind of mixing the coordinates. So we have no mixing term, or term which depends on one only. I think if it depends on one only, it would be fine, but the mixing is a problem. So then we can separate in this case, and we then solve two equations. Usually, in this case, they look exactly the same, of course with different constant. And then the solution is just these plane waves which are propagating along the string, okay? And this is a standing wave which basically stands and then oscillates up and down. And we can get from this the solution. And then in the atom, essentially the electrons also is a standing wave which oscillates like this. It is like on the ring. Like if I take this string, if I take this and put it on the circle, this is how the electron oscillates in the atom. It goes around. It's like a cylindrical cavity where the electron goes around and oscillates. Okay? It's clear, right? Very simple. All right. So, I mean, the Schrödinger equation is not exactly the same like this wave equation. It is linear in time, but except of this, it is very simple, similar, and the solutions, if we neglect this time dependence, it looks very similar, and it gave us again this superposition over these eigenmodes, like in this case, right? We have these, the complete solution is a product of the x-dependent part, the time-dependent part, the x-dependent part, and then because it's a linear equation, we can superimpose over all these solutions, and the superposition is also a solution of this equation, and we get basically the solution of these musical instruments where you have these harmonics playing together, right? So it's all together. And the Schrödinger equation is also like this. It's designed like this. I don't know if it's exactly correct, but it's designed like this, and then it also, every superposition is a possible solution of the Schrödinger equation. Okay? Okay. I'm going to check. All right. so far so good. So this is math, I will skip over it. Okay, again, math, whatever, I don't know, you need to look on it. So these operator equations, right, operator eigenfunction is defined by, when we apply the operator on the eigenfunction, it is the same eigenfunction multiplied by a constant, right? For Hermitian operator, this is a real constant, okay? And then we have some properties of the Hermitian operators, right? That two, I mean, the most important problem was this one, that operators that commute have the same eigenfunctions and vice versa, right? That those we used a lot in all kinds of systems. And then we can construct also the complete basis set from all the solutions, all these eigensolutions for a Hermitian operator form a complete basis set. And if I have, if I then pick any function which has the same boundary condition, then it must be possible to represent it through this eigen solution, which is complete. Right? The completeness is very useful because it means that any function, I mean, I'm not trying to think about those very crazy functions which mathematician can invent, okay? I'm thinking about some nice functions can be represented like this. Okay, the commutators, we discussed what it is, right? That if I clean here and if I make dirty and clean, it's not the same like if I do it in the opposite way, right? If I make dirt and clean, it's not like if I clean and then make dirt. So these are commuting operations and the same in real life. So if you apply f and g or g and f on function, then for commuting operators it's the same, and for non-commuting it is not. And usually when I have x and derivative over x, they are not commuting, and this is because they are actually representation of the momentum and coordinate, which are not commuting. I mean, maybe I'm kind of playing in around the words here, but that's what we get, right? So this would be like momentum, this would be coordinates, and a particle cannot have the same coordinate and momentum. This is observed in experiment, and it is also represented by this non-commutativity of the operators, of the coordinate and momentum. Okay, so they don't have the same set of eigenfunction, and again in a different lecture, but yeah, here. So coordinate and momentum, because they do not commute, okay, they do not commute, they do not have the same set of eigenfunctions. That's why particle cannot be simultaneously observed with well-defined momentum and coordinate. Okay? Because momentum, well-defined momentum means that it's in a momentum state, but momentum state cannot be an eigenstate of a coordinate operator. And vice versa. Coordinate eigenstate is a well-defined coordinate, but it's not eigenstate of a momentum operator because they do not commute. Okay? It's clear? Yeah. Alright, so see, we are going very fast. Maybe we can do it in an hour. Yeah. I think this is the way how you should understand it, in this interconnected way, and then I don't need million of details, which anyway don't show anything if you don't understand the connection, you know. All right, so then we started to discuss the Schrödinger equation. Again, by some intuition, we wanted to have it linear and first order in time for simplicity. I'm not an inventor, I'm not going to tell you why exactly, all right, but they wanted to have it simple, and this is the product which we obtained from the analogy of the results which we get when we differentiate a plane wave. Okay, if you differentiate plane wave, first order derivative spits on us the energy, and then if we compare energy and second order derivative over the coordinate, we get momentum square. So then you get the comparison energy momentum square. So we get the Schrödinger equation. This is the time dependent Schrödinger equation. Okay, so the classical wave equation has second order derivative over time here, and the quantum wave equation has first order. Okay. All right. then we use these correspondence rules. Then basically we can use these rules by assigning every classical observable like momentum, energy, angular momentum. We can assign some operator the same way like we did it here. Okay, energy we assign basically this operator, you see, and then momentum we assign this operator, right? Because we assume that when you apply the derivative over r, it spits on us momentum, so this looks like an eigen solution of a momentum operator. That's why we use this kind of rule, right? So then we use these correspondence rules also in other cases, right? When we constructed angular momentum, we use this rule to construct angular momentum square and everything. Okay, I will not discuss these details, how to do wave functions and so on. This is all clearly discussed a million times. The probability, how to calculate probability density of the particle okay, and so on. So this is the time-dependent Schrödinger equation. When the potential is time-independent, we can separate it. You remember we had a case actually in the spectroscopy where we have external field which depends on times. This is exactly the case where we cannot use this, right? We cannot separate the Schrödinger equation in the time-independent and time-independent component when the external field depends on time. Because then this potential depends on time and we will not be able to break it in pieces, and then we have to use different approach, somehow perturbatively. So, right? Okay, but if we have a potential which doesn't depend on the other variable, like the time here, if it depends only on one variable, one type of variable, the coordinates, then we can separate it and we can proceed the same way like in the classical wave equation. We can look for a solution which are written in this separable form, and eventually we get these two equations with a separation constant, one which is time independent and one which is time dependent. Okay? The time dependent equation is trivial to solve. We just integrate it. Okay, so we just put d phi over phi. On the other side, we put dk and integrate it and get from this that phi is exponential function. This is true for every Schrödinger equation. As long as we separate them, this solution for the time-dependent part is true for every Schrödinger equation. Okay? Now the question is how to solve this time-independent part, and obviously this is the eigenfunction problem for the Hamiltonian, the quantum Hamiltonian, which is obtained by the correspondence rule from the classical Hamiltonian, right? So this is this equation, and the eigenvalues are essentially the separation constants, right? So then I want to solve this problem for the eigenfunctions of the Hamiltonian, and the eigenvalues will be the separation constant, which I can then use to obtain also the time dependency. Okay? Okay, so, and then again, after I find the complete basis set, complete set of solutions, okay? So then I can construct, I can write the solution by the time, like a product of the time dependent and time independent for like this. And then the most general wave function would be a superposition of all these possible solutions which I get in this way. Okay? It's the same like in the classical wave equation, except that now we are solving Schrödinger equation. Okay? And again, it is possible because the Schrödinger equation is linear. Okay? So that would be some kind of time-dependent wave function. Typically, it would be some wave packet which is moving in time and space. One thing which I was repeating a number of times is that if there is only one term here in this wave packet, so basically it's only one, something like this, right? Then if I calculate the probability density square it, then this constant is gone and the wave packet is not moving in space. But if I have more than one, if I have two energies already, more than one components, then the time dependency is not cancelled, and each of the components have its own evolution, and then it starts to jiggle in space. Okay? So energy eigensolution are not moving in space. This is like basically the orbitals in molecules, right? They are also not doing this in molecules. They are static, right? Because they are eigensolutions. These wave packets, these orbitals are like basically static solutions, right? And that's why, for example, in molecules, in molecule what happens, they adjust in such a way that that eventually, like two orbitals slightly shift so that they get degenerate in energy, and then they stop jiggling, okay? And then it's basically all in the molecule basically static. So that's how the energy is also shift, so that it is not moving. All right, I don't know. Is it clear enough? Yeah. So you see the connection which I kind of talk about, right? Where you see from one thing to another, and all right. So then we started to talk about a couple of problems. I will just run over them very fast because there is no need to discuss them more here. I know plane wave solution is obtained for free particle potentially zero, so we have superposition of two plane waves as the solution of this. And in fact, we can integrate over all the possible energies, right, in the solutions. I mean, all the possible plane waves are solving this problem with all the oscillatory, right? K can be anything, and the K is connected to the energy like this. So the solution of a free particle is a superposition of infinitely many plane waves with arbitrary K. What is interesting here actually is that in this case of free particle, the momentum operator, the eigenfunctions are also eigenfunction of a momentum operator, because in this case the eigenfunction of the Hamiltonian are actually eigenfunction of the kinetic energy only, and the kinetic energy is momentum square. That's why the momentum commute with kinetic energy, that's why the eigenfunctions are also eigenfunction of momentum in this case. Okay, but not in other cases, because then the Hamiltonian would be also potential energy, and then these eigenfunction would not anymore commute with momentum. Okay, yeah. So I mean, all these discussion like three-dimensional cases trivial, right? We just separate the variables if it's possible. In some cases, it is not. Okay, if you have some kind of constriction, for example, like cavity with arbitrary shape, obviously you cannot separate the variables. Then you would have to solve it all together. But in some cases, like some kind of boxes, you can separate x, y, or z, or if it's a ball, you can separate the radial and angular, and so on, right? It all depends on the shape. But yeah, so in this case, it's a free particle. We can separate x, y, z, solve it like a product of all these cases, and that's the solution. Yeah, this we discussed the uncertainty that the momentum is perfectly defined in the plane wave, by the coordinate is completely undefined. The particle is everywhere in space. Okay? Alright, so for the particle in box, it is basically a musical instrument. You have basically some kind of space where the quantum de Broglie wave is oscillating, and you have just a half integer multiple of the de Broglie wavelength fitting in the cavity. That's all. Okay? And then you just need to calculate what this is, right? So this is trivial. We just get from the quantization the fact that the solution here is free particle in this region only, and this is a sine function or cosine function And so from the condition that cosine or sine, I think in this case it would be cosine if it's 0 is here. If it condition that here is 0 and here is 0, we get this, okay? So one of the two, it depends on where we set the coordinate beginning, okay? And then we have Ka, which is in the argument, must be n type pi to have the 0 here and 0 here. Okay, so those would be the quantization kind of K, which would be the momenta or multiplied by h bar momenta of the free particle when it was here, if it was here. And the energies associated to this would be those, right? This is like kinetic energy. If I put this here, right, and divide by 2m, it's a kinetic energy, and those would be the energies of the particle. Okay, so we get it here, and that's pretty much all. But just maybe to remind somebody, or most of you, right? We normally, when we solve such a problem, we separate it in the regions which we have, which the system has, right? So in this case, we have region 1, region 2, region 3, and we solve the Schrödinger equation in these 3 regions, and then we need to connect it so that the wave function at this point has the same value on both sides and the same derivative. Okay? In this case, it's trivial because here it's infinity and the wave function must be 0 and here too. But in more general cases where the potential is finite, then you need to connect it in the particle tunnels in this region partly, right? Yeah. I was still able to absorb, or is it too much? It's a lot, huh? Yeah, that's why I think that 2 hours cannot make it, but I don't know how to do it. Maybe we can do it on some kind of Skype, you know, but I don't know how to do 100 Skypes. Yeah. Okay, so then we have the uncertainty of particle and of the coordinate and momenta also, and neither of them is 0, but the product of them is kind of constant. You see this one cancels, and it doesn't depend on the width of the cavity. And it is larger than 0, the product, because we cannot put it infinitely defined any of them, or both of them, yeah. Okay, this is the 3D case, again the same like for free particle. Again, the separation is not always possible. If I cut the plane from this point to this point and this point, you will not be able to separate it at x, y, z, right? It's only possible if I have a cube like this or some other shape which is separable. But yeah, so then this is the way when I cut it like a box. How are you doing with time? Yeah. All right, so we just passed the simple systems. Oh, this is still here. This is very slow. How about if you need some morning, like early morning, you don't have time this week? Is there no single hour where we can meet? I don't mind to be here at 8, 9, 10, 11, anytime. Why? No.
I'm making sense, so I can't.
Nobody? No? I don't know, I think it's not good. Okay, so, yeah, I don't know. I need to find something. Okay, so then this is the superposition, right? We discussed this is the wave packet general in free particle, and we discussed that if we want to measure, for example, well, I don't know. I mean, in general, this is about measurement, but I don't think it's so much important for you. You just get if you want to find in which of these eigenstate the particle is. In fact, it is in a superposition, but if you want to find in which of them it is, we will find with this probability that the particle is in this state, okay? So for different, the constant actually gives you the probability. So the square of the constant gives you the relative amplitude of the particle, okay? And this gives you the probability if you measure. But you will get each time different results if you measure. Okay, those are some of these interferences. Yeah, I mean, this is the Heisenberg principle, which is essentially related to the fact that two operators do not commute, in this case coordinate and momentum, and because of that the uncertainty product of those two operators, the square, the uncertainty must be larger than 0 and it is equal to some expression, okay, in general. Yeah, so then we discussed briefly tunneling again. I would certainly ask maybe something about tunneling in general so that you know what it is. So classical particle cannot penetrate a barrier which is larger than its energy, but quantum can, and if the barrier is narrow enough and not so high, then there is a chance that a particle can go through it, and the wave function, which is kind of free before the barrier, become kind of like decaying inside, because we will have a real exponent in the barrier rather than oscillatory. It's about this solution of the second order ordinary differential equations. When the coefficients are positive or negative, it gives you this solution or this solution. So in this region, it basically decays, and here again it oscillates. And then we can calculate the probability of going through if the energy is smaller than the barrier, and eventually we get this exponential probability below the energy of the barrier that shows that particle can penetrate the well of length L and energy of barrier height like this by this in this transmission probability. Okay. So both the length of the well and the height of it enter in this expression. Yeah, I mean this I will not go over, but actually this is the most important for the exam, because you will probably have some quantum well problem. Okay, so you go over it and try to solve such problem. Okay, just check it how we do it step by step. To do it all the steps. Okay, so we have several regions, 1, 2, 3, and then we solve it in each region and connect the solution in each point, and from this we get the constants which are necessary for the solution. Okay? Yeah. So I mean this is a dependence. Yeah, this is double quantum well, again very illustrative example, because it's similar to molecules, diatomics. So this is the ground state of the diatomic, this is the first excited state of the diatomic, right? It's exactly the same problem, except of the shape of the potential, which in diatomic would be 1/r. Here it is just a square. Okay? Yeah. And again, this is we can, in first approximation, we can superimpose wave left, wave right, and this would be the linear superposition of atomic orbitals giving the molecular orbitals. So basically, right, whatever we use in molecules, you can already do in double quantum well. First approximation is the same solution like for molecule. Okay, yeah, you see this is the molecule. Yeah. All right, so I'm done with this. I don't know how much more time. Then, but can we stay at least until 3? I mean, try. Yeah. Okay, quantum harmonic oscillator, same like classical. Frequency is the same like classical. This is the frequency. Obviously, we take the classical Hamiltonian and replace the kinetic energy by the kinetic energy operator square, right? And then the solution is very simple here and very beautiful, because the energies are actually equidistant. Okay. So these are the eigenenergies, equidistant, and the wave function look like in a simple quantum well, except that they need to kind of broaden with the energy. So then they have slightly more complex form, but they have again this nature of even, odd. Because the potential is symmetric, then they must be even odd, okay? And that's all, right? So there is nothing more about the harmonic oscillator, except that we can play with it. For example, here we can construct these coherent states which are semi-classical in nature, where we can basically represent some classical motion which we are used to in harmonic oscillators. Now, if we have anharmonic oscillator like in molecule, right, we have been discussing them also lately for the statistical mechanics, for example, then we solve it again. We can approximate the exact potential. This is the, right, you remember we get the, if we have diatomic, we have the U function, the potential energy surface. This is the potential energy surface, the ground state potential energy surface. We can also be excited. If we take the ground state potential energy surface, we can approximate it and then solve the eigenfunctions. If we do it exactly, these are the eigenfunctions, the vibrational states. There is only a finite number of them, then there is the dissociation, and they are not equidistant. Okay? The equidistancy is lost because of the anharmonicity. Okay? And then if we approximate it by a parabola at the bottom, we get the same kind of behavior at the bottom, and then we can approximate it in such a way that dissociation is also the same as dissociation energy. So we get this Morse potential. Okay, this is essentially the association of vibrational, rotational states together. I mean, I don't need to discuss it. Okay, so we didn't even, oh my god, we didn't even get to hydrogen atom. This is just impossible. I'm not trying to go so fast. Okay, so then rotation we discussed as much as possible. So can you talk to each other and try to invent at least one possible solution for 1 hour that you can do? Is there not possibility? At least majority of you, and then you can share it with each other, you know. Just send.
Is there any way to post what you cover on Blackboard at least for those who can't?
Yeah, but I mean, maybe you can guys record it, one of you, right? Somebody was recording our, so you can record your hour, and then you can share it between each other. Okay? I guess that would be good. So send me an email when you can meet for an hour or two by Thursday, including Thursday. Right? Thursday. Oh, Thanksgiving. So Thursday is not still a Friday? Oh, I thought only Friday. Okay, so send me some email when you can meet for an hour or two anytime during the day, and except the normal hour, and we will probably need 2 hours. Okay, and you can record it by some cell phone and then share it so that not with the whole universe, just between the two. Alright, so I need to finish because you are talking, I don't make any. So, okay? Potentially send it still today, maybe we can meet already today, maybe tomorrow afternoon, tomorrow morning, Wednesday, okay? Send it to me, just agree on the time and we can do it, okay? We need to do it. I'm sorry. Anything else, Google?